Okay.
This is interesting.
Is there audio now?
I don't know.
What do you mean you don't know?
Well, nothing's coming up.
Awesome. Okay, that works.
Oh,
Nice.
just because of that.
Oh, there's stream delay. Awesome.
Oh.
Wait, can you keep that?
You want
Can you
me
keep
to
that
do
up so I can see what's up? You're my second monitor for a little bit.
I'll just mute it. I'll mute it.
Yeah, that's fine. Okay.
So you want to see this the whole time?
I need to see it for a sec. Okay. Because I just want to know where the camera ends up. It's awesome at the top right.
You can you turn the camera off? Or do you want to be
I
seen?
want the camera.
Okay, you want to be seen.
Okay. Should we start in 2 minutes or start now?
MIT time.
Just start chatting.
Mhm.
I have to start talking. Hey guys. How's it going? Have you guys I want to gauge people's experience with CAD. Have you guys done 3D modeling before? I get like a show of hands who's used Onshape. How about SolidWorks? How about Fusion 360? All right, that's good. Is there another CAD software I'm thinking of? NX. NX is a good one. So today I'm gonna teach you, like, as the description says, CAD for hackers. You only have 24 hours to actually build your thing, so you need to maximize that time as much as possible. So there's things like, it's a lot of designing to cut corners. You're not going to learn this in school because this is inherently not very good design practice, but it will get the job done in the time frame that you have. This skill set is actually like if you do this in industry, you will get yelled at, but if you do this in the startup world, you will get praised and they'll be like, "Wow, you made this so fast. This is so awesome." That's the thing I'll be teaching you today, how to CAD something really fast. I'm gonna wait for a little bit more. Are there projects that anyone's like interested in doing? Anyone have like an idea or vision on what they want to make? Do you have one?
No, we're not together, so
Oh,
doesn't want to speak it.
keeping it secret. Keeping it secret. All right. Is there a track that you're interested in at least?
Yeah, no, not yet. I think we need to brainstorm with the others.
All right. Okay. So, do you guys have Fusion 360 installed at least? It's fine if not, because like I'll be moving pretty fast, and like if you guys need help, it's good if you guys want to like follow along, but it's also not really necessary. Do you guys have experience with different tools? Let's say 3D printing. Do you guys have experience with 3D printing? 3D printing, laser cutting, machining, like CNC machining, metal machining, mill, lathe, that sort of stuff? All right. So maybe I'll just brief over the tools that you'll have access to at this event. So you'll have access to tools like metal laser cutters, 3D printers, normal laser cutters, mills and lathes, and then plenty of woodworking tools. This workshop primarily is designed around using the metal laser cutter, and 3D printing as your primary fabrication methods. But you can also design around like metalworking if you have experience with that. Because Fusion 360 also can do stuff in metalworking with CAM. CAD and woodworking is kind of like, I don't usually do CAD and woodworking at the same time because woodworking is kind of, in my opinion, it's more freeform. That's also not necessarily true. You can make pretty precise parts with that. Okay, so the first thing I want to go over when you're doing bad design practice is that Fusion 360 has a thing called hybrid design, which enables this, right? You can make both parts and assemblies in the same file, which is like really good if you want to move super fast. But also in industry, what they'd want to see is you make an individual part in a file, and then once that part is locked in, then you can put in an assembly at the end of the day. But today we're just gonna make everything in one file. The timeline is gonna get pretty messy, but we're gonna try our best to make it like still workable. What I'm gonna start with is I'm gonna show you like how you can go from an idea, straight from an idea to a CAD model in like a couple minutes. Along the way, I'll talk about different strategies I use to enable going fast. So real quick, I'll do this and then I'll whiteboard up a design. So, all right. So let's say I want to make a 6 degree of freedom robot arm, right? The scale would probably be like this big-ish. I would do things like, let's use a circle for motor. And then I want a linkage here, a linkage here. So if people don't know, a degree of freedom usually translates to like 1 motor is 1 degree of freedom. So for 6 degree of freedom robot arm, there'd be 6 motors in the system. So let's say this one points in this axis of rotation like through the page, and this one is like maybe joints like it can go left to right or something. And then maybe we have one that is like a turret that this sits on. And then let's just keep tossing degrees of freedom on this, and then the last one will be like a claw or something. This is like a rough sketch, but you kind of get the vibe for what you're making as long as you move forward, right? At the end of the day, I just need something with 6 degrees of freedom that might be able to like pick up, grab stuff, something like that. So my end goal that I want is a 6 degree of freedom robot arm that can maybe do pick and place things, right? Maybe I pass it off to a software person on the team, and they can just like work on software with this model with this robot arm that I designed in like an hour and fabricated it in an hour. So they're not just waiting around for something to be built while working on software, right? That's part of the reason why you want to go fast, so that software can get started as soon as possible. So let me show you how you can design this like really fast. So first of all, you need to figure out what motors you want to use. The easiest place to find CAD of motors is GrabCAD. So here's GrabCAD of a servo motor. This is just like a standard servo motor. We have a couple of these, maybe not this exact dimension, but you could use something like this for whatever project you need. So for a 6 degree of freedom robot arm, this is perfectly fine, and it has enough torque. I've already imported it in, but you can import it by upload select files and toss it in. So I have this servo motor. I can just drag and drop it in. So this is the move menu. What I like to do is I like to rotate it to the position that makes sense. So I'm starting with the turret. This is the move point to point command. So I can move from this circular point to this point. So now it's like centered around the origin, which will help me later. It's also not necessary. And I can hide the origin over here. Actually, before I begin making the entire robot arm, what are people's proficiency in CAD? Have you guys ever CADed before in general? So everyone here has CADed before in general? No? Okay, so I'll quickly go over the basics. So pretty much any item can be made with a summation of extrudes and revolves and cuts, right? So let's say, let me find an item that I have. Let's say I want to model my water bottle, right? This is like a cylindrical object with a weird shape at the top. Let's say I want to 3D model that. I would start with a sketch, and I pick a sketch plane. Easiest one is this. There's 2 ways to design this water bottle, and I'll show you guys both ways. With a revolve or with a couple of extrudes. So let's say I wanted to design it with revolves, right? This thing is about 5 inches tall. I know this because I've measured my limbs before, so I could just put it up to my arm and kind of guesstimate how long something is. This is actually, yeah, probably the part up from this cap to this part is, actually, I think I'm wrong here. No, yes, probably about 6 inches. This is just a quick and dirty CAD. This line will be my center line that I'll extrude around. Let's say the base is 1 inch long. I'm designing in metric because metric is a little bit more useful for other stuff, but this is still like doable. So the keybinds I'm using are like keybinds. L while you're in a sketch is line tool. You need to like lock in all the keybinds if you want to design really fast. And something to note is you want everything to have like, you want all your lines to be white at the end of the day. That means your sketch is fully defined. I'm looking at this looks like a maybe like 30-degree angle. So let's see, this is 90 degrees, so this would be 120 degrees. And then I use D for the dimension tool. D while in a sketch, dimension tool, which allows me to define how long this is. But look, this is also not defined. So I'm gonna click both this line, and I'm gonna press E. E is a constraint. E sets two lines equal to each other. If you don't want to use like keybinds or something, the constraints are up here. These are important for keeping things like, you don't want your lines to be blue at the end of the day. And then I'm gonna put like 40 here, so it rounds up to a nice number. And then I will finish off this shape. Looks like it tapers up a bit too, so let me do that. Go up here. Okay, so now I have roughly the shape of my water bottle minus the top cap part. So what I can do is create, revolve, click these two parts. All right, revolve, axis is selected, profile, and then I'm actually gonna right click down here and I can edit the sketch because I want these two to be one shape. So what I did here is I clicked it and turned it into a construction line by pressing X, or you can also do it here. A construction line does not affect your final like extrude or revolve geometry. So X is construction line. So I clicked it and clicked X, and that's how I got that. So now it will no longer affect the revolve. So I could just click this profile, and now I have roughly the shape of my water bottle. Let's say I want to do the cap. This one doesn't make sense to do revolve because it's less cylindrical. What I would probably do here is a summation of extrudes. So let me just extrude this like 1/2 inch for the little bottom part. What I want to do here is I want to create it as a new component, so it's not combined with the previous component. And then I want to create a sketch, but I want it to be in the center point, and I'm going to do this like weird triangular shape here. So I need to project this geometry because I need to reference this geometry, and I'm not in the correct plane for it. So what I did there was I clicked P and then selected that line. I could click P and then like select all of this to get the entire geometry, which will be relevant. Some of this geometry is not relevant, but P is project geometry. And then let's say I want to do this shape now. This one is mostly just guesstimation because I don't particularly feel like measuring it right now. So I have this, but I want it to be like, I want the hole in the center, right? This tool is called the offset tool. I can just click this line and then drag it in a bit. So let's call it -10. And then I need to extend this down because I want these to intersect. So I can select this dot, select this line, and I'm like, I want these lines to intersect. The tool for that is called coincident. So you can just click, coincident, and now you'll see that it's all blue here, so it's underdefined. You could just, what I like to do is just round to the nearest like 10th. This helps when if I want to change the numbers later on, then the geometry is like a little bit nicer change. So now you can see it's mostly constrained, except it can wobble. That's not what I want. So I need to constrain the angle too. So let's constrain it to 130. Now roughly that shape. Now I'm going to do a symmetric extrude because I'm starting in the middle. There's multiple types of extrudes, but what I did there to go to immediately to the extrude tool is Control plus E gets you to extrude. And then you could type in a number. There's different types of extrude. There's one-side extrude where you extrude one side. But what I want to do is a symmetric extrude because it's roughly symmetric. So now I have this, but you might notice it's not curved yet. So what I can do now is Shift plus F is the fillet tool. The fillet tool is like the go-to on making things look nice. Okay, you just Shift F, select the edges, and then select every edge that needs to look nice. You always fillet at the end because playing around with fillet geometry is a little harder, and then you can type in numbers until it looks a little nicer. 5, 6. So let's call that like 9. And then I actually want to edit it and put in another fillet for the other edges. So I'm going to select here, here, pretty much all the other edges on this face. So now it's more rounded out, and I can keep playing with the numbers until it looks better. And let's say I also want to do the inside a bit as well, but maybe a little bit less. So I'm clicking this plus sign when I want to add another fillet of a different size. So I have this. Doesn't look exactly right because the hole in the center is like much larger, right? So I can go back into the sketch and just the number I need to change for that is the offset. So now it's smaller. What's going to happen is the fillet's going to break because it's like not able to do that, and it looks like it's this one that will break. So sometimes you might just need to go in and redo the fillets entirely. So let me just go ahead and do that. There we go. And then the inside, 2, and then over here, it's like 4, why not? And then maybe I want to have it like this. There's some weird behavior happening here, which I can just kind of fix with the fillet as well. And then you kind of just play around with numbers until something works. There you go. So this fillet also broke, which I'll just delete. Okay, so you can see like rough model of the water bottle in just a couple of minutes using revolve, but say I wanted to do it with extrudes instead. What I could do is just do a circle, let's call that 2 inches, extrude. So I use the C tool to get to the circle, to just start drawing a circle. So C, circle. And then like if I click C and then drag, and then I could type in whatever number I want and it'll work. Shift E, extrude up, and then what I can do here is Shift E, create a new body for like that top. Maybe you don't want the taper. You can get the taper in a couple ways. One of the ways is using a chamfer, or you can just do it originally in the object and do that to get the little taper up here. And then you can Shift E off this surface, keep going up. Now you have the second part of it. And then again, if you want to do this little like triangular part, you do a sketch in the center and just go ahead with that. Like you saw before, I just did that. But now you see it's not connecting to anything because I need to project geometry. And then control, press coincident, and then maybe I could just drag it and it locks in. Do some angle stuff. Yeah. So similar situation of that's how I would CAD a water bottle. Like speed CAD a water bottle. So at the end of the day, most geometries can be done with a summation of extrudes and revolves. Let's say, for example, though, of course I need the water bottle to be hollow. So let me go back to this one that's a little bit more done. I can hide the cap for now. There's a couple more tools in here. What would be relevant here is the shell tool, which pretty much hollows out the entire thing, hopefully. Yes, so now you can see the water ball's entirely shelled out, which means it's hollow. This is section analysis. It's in the inspect tab. You can click here and you can see the inside. You can see it's hollow. For water bottle cap, you can do the same thing. Of course, water bottle cap needs threads. So there is a thread tool, which is here. You can just select and it can create threads. And you can play around with the numbers if you need to. That's quickly what I want to go over with like just basic CAD, summation of extrudes and revolves. Yes? So if you want to use the thread tool, create, let me actually delete the first thread tool. So let me first, I want to like have access so I can actually click on it. So I'm going to hide this component, which is the cap. You can always rename cap. This is rename bottle. I like to keep things in components, so I can right click, create component from body. But now if I want to create a thread, it's create. There is the thread down here, and then just click the cylindrical surface with the thread. Yeah, and then you can play around with this and play around with the size or whatever, and it'll like sort itself out to what makes the most sense. Okay, so that's that. That's the water bottle. Let's say now I want to do like a robot arm, something a little bit more complex. This is where I'll like talk about design around manufacturing, because making that water bottle is not really realistic. It's aluminum. It's like, I believe what they do is like they blow mold it or something out of some really hot aluminum, or they do it on a lathe. I'm not particularly sure how that water bottle specifically is made. But in context of what we would be able to make in one day, a robot arm is doable in like 2 hours if you know exactly what you're doing. So first of all, I need to mount this bottom servo to something, right? I can't just have it like a servo, or else it'll just fall off the table when I'm playing around with it. So let's start with the base. I'm creating a sketch. The sketch plane I'm starting with is actually the bottom here. And let's just do a good old circle. Now what I want it to do, what I'm envisioning here, is that the circle like slots into the servo. Like the servo slots into the circle, right? So what I'm going to do here is I need to get the outer face of the servo so that I can do that. So I'm clicking on the outer edges. And now I have this rectangle. It's not closed because there's a fillet here. So what I'm just going to do is just close it off. And then I pressed G for the rectangle tool. So rectangle tool. And then of course I need this to be coincident as well. So, or collinear. I want the two lines to be inside of each other. So that's a constraint. Anytime something's blue and you can move it around like this, that's generally not good. It's not good design practice, and it'll end up biting you in the back later on. So I'm gonna make sure to, you can spam escape to deselect stuff. So collinear, this line to this line, and then collinear, this line to this line, and now I have the rectangle, right? So now I can Shift E, extrude this. I want to extrude this. Let's say I extrude this. The distance I want to do, I don't actually know. So I'm going to use the to object command and select up to this bottom face of the servo. And then new body, I actually like to work in the component realm. So new component, bodies and components kind of just like, if you stay always in the component realm with this sketchy hybrid design thing that we're doing, you'll probably be fine. So now you can slot the servo in, but there's one thing to keep in mind is where's your wire going to go? So the wire was on the left side. If I hide this, you can see there's the place where the wire would go here. So I'm going to create a reference line that goes all the way out to the edge, and then I'm going to create a rectangle that will just help me out here. So all the way out here, and I'll give it a distance. Let's call it 25.4. And then these two are coincident. So now I can extrude as a cut now. So if I extrude in the negative direction where there's already material, then that will be considered a cut. So cuts here. If the servo motor was not a component from like a different file, sometimes it'd cut into the servo motor, so I might need to drop down and like select what actually needs to be cut. Now the servo wire has like freedom to go all the way out. Next thing is figure out what is needed for, I want to screw this down, right? So here is what big fastener wants you to think, okay? Or big heat set inserts, or big whatever, right? That you need if you want threads in plastic, right? Right now I'm designing this giant circle to be 3D printed. If you want to be able to screw something in there, then you need like heat inserts or something. But actually, the first time that you screw something into plastic, just like straight up, it will be just about as strong as if you use another method. If you unscrew and screw it back in, it loses about 20-30% strength. But if you're just doing something once, that 60% strength is good enough for most projects that last a day. So what I did here is I project geometry all this so I can get the center locations of the holes. I'm going to use an M4 screw here. So what I'm actually going to do is design this is 4 millimeters, but I'm gonna force an M4 screw into here. So what I like to do is subtract about 0.3. My rule of thumb, and this is like a general rule of thumb, is say it's if I have an M4 screw, there's a 4 in there, I subtract by 0.3, which leads me with the circle I want to do when I'm forcing a screw in would be 3.7 millimeters. Similarly, M3 minus 0.2, I would do 2.8 millimeters, and then M5, so on, minus 0.4, I would do 4.6 millimeters, right? And then that's like generally the correct diameter to force a screw into plastic and it'll have it work. So for this, I'm going to do 3.7. And I'm just going to create circles, circles, circles. And then I'm going to control click all of them. I've already defined one of the circles, so I can define all 4 of the circles at the same time now. So control, 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 click here, and then I press E, making all the circles have the same radius, or sorry, same diameter. Now I can extrude out all these things, distance to object to the bottom of the circle. And now I can force screws into the plastic if need be. Now here's another consideration. How am I going to slot the object in here, right? So I can't move this object because it's grounded to parent. That just means that it's grounded. You can just unground and now you can actually move it. So I click here and click M to move. So M, move. I can move this up and down. You'll notice that if I want to slot it downwards, it's actually going to intersect with part of the plastic. So what I'm going to actually have to do now is give it a little cutout to not have that happen. So I'm going to select this as the top plane and then center it around the 2 bolt holes and then just kind of just like eyeball it. Let's call that like 5 millimeters by 10 millimeters or like 12 millimeters or something. Actually 4 millimeters probably makes a little more sense. And then I extrude this all the way down again. So now it can possibly, you can now be able to put everything in. Now here's another consideration though. This is designed around the exact geometry. When you 3D print something, it's going to be, ends up being oversized because of thermal expansion, right? So when you try to push it in, it's going to be really, really tight. So there's a keybind for that. It's called press pull. So we use Q, which is press pull, good for tolerancing. So I press Q because I know I'm going to 3D print this part. I press Q and I select all the faces that need to be moved out a bit. So these faces need to be moved out a bit. So I press Q and then select the faces, and now I can do minus 0.2 or minus 0.3 or minus 0.4, however. Usually my rule of thumb for a roughly snug fit is subtract half of the nozzle diameter times 10. So if the nozzle diameter is like 0.2 or something, then sorry, 0.4. You might see 0.4 millimeter nozzle diameter, 0.6 millimeter. You subtract half of that, now you're at negative 0.2. And then this will be a snug fit when I actually 3D print it and slot it in. You can see there's that gap here, there's that gap here. And then one other thing I want to add before I move on to adding the rest of the servos is I want to add a little bit of a chamfer here so that the wires don't get caught or anything on their way in. So this will probably work as is. Yeah, and then I have a lot of room here. So this servo can like sit snugly in here. So now when you're attaching something to a servo, you need to figure out how you're going to bolt something onto it. So servos will come with this thing called a servo horn, which you can kind of just slot onto here. And then let's actually hide this so I can select the bottom inside circle of here. So I click move point to point, this point, and then I'm going to slot it onto here. Well, the reason why I don't use the joint command is because the joint command doesn't play nicely when you edit things in the timeline earlier. So there's that. We have this now. And now we need to think about how do we stack a servo on top of that. So what I might do is take this, or sorry, rename this to bottom mount. Another thing that's sometimes helpful is you press Shift N and then things become funny different colors. Shift plus N, colorize everything. So let's stack a motor on top of here. Sure, why not? Do this, and then I'll center it, roughly center it on the circle here, and then move it roughly up where I want it to be. So right now this is designing around 3D printing. 3D printing is decently slow. The first couple of parts will be 3D printed, but for now I will create a circle around this, hide this. This is 22 millimeters. What I want to capture is the bolt pattern here. They come with their own fasteners. So let's do like this, this, this. Another thing is you don't need all the circles. Usually like 2 to 4 screws is enough for most things because 2 points and a plane define a plane. So let's do that. New component, of course. Let's extrude it up a bit. And I don't actually need all the holes. So I'm going to remove these holes. Another thing I'm going to do is screws have a head size. I need this to be flush so I can actually toss the servo motor on here. So I'm going to do this. The head size of this I'd measure with calipers, like day of. I don't actually have the screw on me right now. But right now, it's only 4 screws, so I'm just going to do it like that and make it go down a couple millimeters. So now the screw head can sit flush on there. Now you might be asking, how do I toss on the servo? By creating this as a rectangle. And then let's make it a relevant size. So I'm actually, for this one, I want it to be 2-sided because I want it to be connect with the part I already did below. So let's make this go down 2 millimeters. Or actually, really realistically needs to be 1-sided, can go down 2 millimeters. I have this servo now. The order of operations, which I need to think about at the same time, is like, how is this going to be affixed to the part? So this green part, we bolted onto the servo first, and then I will take this servo and then put it on second so that it doesn't interfere with anything. Here are my circles here that I can connect to. So what I would do is just have little pegs that stick up. And then let's call that like that. This goes here, this goes here. Of course, this needs to be actually longer, so what I'm going to do is go back to this original sketch and increase this to like 70 millimeters. Why not? This is just a rough CAD design now. And then, of course, again, project geometry of the servos to do what I need it to do. 3.7 yet again, because I'm just going to force the screw through plastic. And then all the way, cut all the way through, distance to object down here. So now this servo can be mounted to this servo, and it will move. Right now I have 2 degrees of freedom. Now, something interesting that you could do like with further links is 3D printing is fast, but it could be faster. So what we could do is design everything around, instead of 3D printing, design it around laser cut parts. So first, hold on, I'm going to fix this. Circular horn again. Okay. So I toss this here. And the next part, when you have a 2D profile, you need to design around, everything has to be 2D. You can't do anything 3D now, but sometimes you want 3D things, right? So for now, let's imagine it's like sort of like a crane for now. So let me just create the bottom point of my rectangle. Let's go 14 here. And then I guess 14 down here. And then I'm going to make these both construction lines because I don't need them later. I press G, rectangle tool again. This is 28, and this is, say, like 100. So this is a part where I need to know my stock thickness. We have a lot of 1/8 inch material, so we have to design around 1/8 inch material. So I'll do 0.125 inches here, because I know we have that on hand. And then what I could do next is, of course, just toss another servo on here with the same process we've been doing. all along. So Control C, Control V, drag this along, and then I might need to move it so that the face is flush. That, and then do the holes again, and then make sure that the wire has a place to go in, similar to how we did like the thing down there. But now, a couple of degrees of freedom. This part is laser cut. This part is 3D printed. Remember, 3D printed parts aren't very strong, so you probably want them to be as thick as possible. So you can go back, Control E, and then like extrude it a bit more, make it like stiffer and stuff, right? So this is like, we're on the way to a robot arm, and that didn't take particularly long. Now I want to show you guys like tricks that you could do with 2D cut things, right? If I want a 3D profile or I want something stiff, let me create another hybrid design. So say, for example, I want one of the parts of the robot arm specifically to be extremely stiff. Let's for now call this 40, 300. (0.125 inches), right? You can imagine I take this giant piece, I could bend it, it'll snap. It's not very strong or very rigid. What you can do is create another rectangle and do like a T-shaped thing. So 0.125 inches. And then you can extrude up like this. Now these are two different parts. It's like an I-beam now. This is maximizing the rotational moment of inertia. Now you think, how do you connect these two parts together? There's a couple ways to do that. One of the ways is design a 3D printed L bracket. So say, for example, I want to do something like this. I'm actually, that's too much. I'm not going to design this very well for now. You can see there's some blue. But I could design a 3D printed L bracket, toss in some holes, and then bolt the two together. Or I could do something a little bit better. I could create a bunch of holes along the center line, and then do something called like a combination of finger joints and like slotting screws. So let's say I want to do this with M3 screws, right? I'm going to start this 12 millimeters down because I just picked that arbitrarily. I want this to be a through hole, so I'm going to add an extra 0.2 millimeters to this so that it can go through. And then I'm going to create a rectangular pattern with this so I can pattern it down. And then let's say I want a bunch, right? 12. This is going to be hastily designed, but I can go all the way through here. Make this go all the way up here. Now I need the second part of this, which is I'm actually probably only gonna do it for like one part. Okay. So I need the center of this line. So I start here. Let's say my screw is 16 millimeters long. That's how long it's gonna end up. I create a rectangle. I want this to be 3 millimeters long. Or sorry, 3 millimeters long, 16 millimeters tall. So a screw can go through it, but now I need space for a nut, right? I'd probably measure the nut or Google the size of the nut, but somewhere along the way, I want it to be able to bolt down. So let's say the nut is 4 millimeters tall and like 10 millimeters thick, which might not actually be true, but I do this, go all the way through here. So you can imagine I have a screw, it goes all the way through, a nut goes here, and then the screw goes all the way down and it tightens through. And I can take this and pattern it along the entire surface if I wanted to. So there's a pattern tool for rectangular pattern, and you could do it for features if you wanted to, and then like pattern it all the way down, if that makes sense. That's how you could get something stiff out of something two-dimensional. That's for designing around 2D parts, right? This is 3, this is not. This is just quickly designed. You would want these to, of course, match up, and you could do that with the pattern tool. Let me check what else I wanted to go over. So that's working around 2D things, working in like just quick rough things. I told you about designing for stiffness when you have a 2D profile. I told you about designing for tolerancing with 3D prints with that 0.2 millimeter thing. Let's talk about torque transfer. So let's say hypothetically, this is something that a lot of people get caught up on. Let me just design a motor real quick. So this is the body of the motor. You can imagine that's the body of the motor. And say it has like a shaft of some sort, right? Let's say this part of the shaft spins, and for whatever reason, it's circular. How do I connect something to this shaft? There's a couple of ways to do that, and leveling on like different levels of like sketchiness. The easiest way to connect something to a shaft is you take a file or sandpaper or grinder and you grind in a flat part into it. So let's say I was able to do this with a file. Now I have a flat part. Now that you have a flat part, things get a lot easier. I can 3D print my own hub for this. So I'm just going to put in arbitrary dimension. This is 3D printed, so I'm going to add an extra little bit so it slots on, and then make this go all the way down. And I actually want this to be a new component. Oh, actually, that's fine. But the issue now is, how do I prevent the two objects from slipping, right? Because since I'm grinding this down, I actually don't know the profile of this. How do I still prevent it from slipping? The easiest way to do that is with a set screw. So let me create a plane so that I can, because I can't actually select the surface to start creating a circle from it. So I have to create a plane. I can create a tangent plane, which gives me something to select. Then select up here. I want to find the center of this, so I project geometry the two edges of this, and now this gives me this geometry. This view cube allows me to move around. I'm going to create a construction line between this, and let's call this 2.8 millimeters because I'm going to use a 3 millimeter screw. All the way down, cut all the way down. And then let me go back. I need the plane again because I want the screw to sit flush. So project geometry because I need the circle again. And then the screw head of an M3 screw is like 6 or 7 millimeters. And then it goes 3 millimeters down. So now it can sit seated. The screw goes all the way down and tightens against this. Since this is undersized, it won't untighten itself. A quick way, if it ends up untightening itself, like maybe you unscrewed it and screwed it in way too many times, you lost all the strength, is you take super glue and you put it on the thread, and now super glue will keep it in place. So that's how you connect something to a shaft. You can, of course, do a bolt hole pattern if you want to. So let's create a bolt hole pattern real quick. Let's call this 3.7 millimeters. Maybe we'll use that and then create a circular pattern. There we go. And I actually might, since there's a set screw here, I kind of want this to be offset. So I could double click on the center and select this. And that should work. So now it's offset from the screw that's going through the center. And now I'm able to use this hub to connect whatever else I want up to this motor, right? I could put on a 2D profile, I could put on another 3D profile, I could put on whatever I need, and this print doesn't take terribly long to do. Something else now I want to go over is designing around 3D printing to maximize speed. So actually, this is a pretty good example. So this part will need to be 3D printed. So what I did here to delete everything else, or not delete, is unhide everything else, is I right click, click isolate, and now everything else is hidden. I can just look at this. Actually, this ends up being 3D printed pretty well because you just 3D printed on this face and 3D printed up. But let's say I have like some weird geometry up here that means it can't be 3D printed straight up, right? Normally I'd want a 3D printed flat, but now I have this rectangle here, doesn't print well. So the next most flat face is the bottom face. But now we have like some weird geometry. To help it along, 3D printers like 45-degree angles, so you can use the chamfer tool to help with this overhang part. Of course, the overhang won't turn out perfect, but it'll still be a little bit better. Let's unisolate this. Let's see. Most of these are actually pretty easy to 3D print. But yeah, for overhangs, you could do that. If I just have like a giant rectangular block, another 3D printing trick is filleting the edges makes things print slightly faster. So when you think about 3D printer and it does a corner, it will just go fast and then just stop and then go to the next angle. But now if you get a fillet, it kind of does a smooth angle in and it just prints ever so slightly faster. There's 3D print optimizations you can do in the slicer as well. I won't go over that today. Let's see. When you're designing around things, think about like torque transfer, how you're going to do that. One more thing I want to go over is designing around sheet metal, because we do have a metal laser cutter. So you want to think about how you're going to bend things. You can do a lot of things really fast. So you saw earlier there was some object. This is the motor. There's like this object, which is 2 pieces in a T shape. You can kind of do something similar, but not really, with like 2 pieces in L shape. So I'm going to start with a rectangle. But instead of going to the normal like Shift E extrude, I'm going to go to sheet metal. And then now that in the sheet metal menu, I can flange this. So steel inches, maybe it's not steel, but you can change the sheet metal rules here. So sheet metal 1/16 of an inch. More than likely, actually what's going to happen is we have plenty of aluminum. So go to aluminum. Now that it's set to aluminum, you can change the thickness. 1/16 of an inch, 0.063 makes the most sense. Now you can do things with the flange tool and have it. The flange tool will be how you can create geometries, right? When I want to export this for metal laser cutting or whatever, and of course, while I'm here, I can also go back to the solid menu and create like holes and stuff through the part if I need to, right? I can go to, let's see, create flat pattern, select the face, and now this is what I need for 3D printing. So this is my flat pattern. I right click, activate, and now this is all I need. There's 2 ways to get this. You can P, project geometry, click OK, creates a sketch, and then you can export this DXF with the sketch. You can also export it here. If I'm exporting, say I want to laser cut this block somehow. You can click on it, create sketch, press P. Now you have all the geometry points. Right click the sketch, export DXF, and that's how you get a DXF out of this. Instead, let's say I want an STL file, or sorry, a step file for 3D printing. I can right click this and then create components from bodies, because you can export components, export step file, and then I'll have all this stuff. Let's see. I want to do, so that's pretty much like a couple of the quick ways. If you want to go really fast, design as much as you can around like 2D laser cutting. So honestly, like, let's go back. Let's go all the way back to, let's go all the way back here. This thing will actually take a incredibly long time to like 3D print, probably like a 2 or 3 hour 3D print. So what one might actually want to do is, I'm not going to delete or remodel this. I'm just going to project the geometry because I have the geometry. Right click, remove this bottom mount, and then let's design this around. Let's design this around 2D laser cut acrylic, right? Now everything can slot in, but you can see there's the issue. It still sits on it still sits on this servo. The easiest way to do that, to fix this issue, is let's create a base. So circle tool, construction tool, go over here, create another circle. This one needs to be a through hole because a bolt's going to go through it, and then through a standoff that we're going to design in a sec. So let's call that 3.2 millimeters. And then create circular pattern because I want a pattern of bolt holes. Maybe I want like 6 of these. So 5, 6, and then I extrude all these down. So the idea is to minimize as many 3D printed parts as possible, but use 3D printing when absolutely necessary. And 2D laser cutting is how you can get things done fast. Next part I'm going to do is I'm going to create a standoff. I'm going to, instead of using the circle tool, because I need to hold on to the standoff while I'm tightening it, I'm going to use a polygon tool to create a hexagon instead. Because hexagons are like, you'll see them as the traditional shape for standoffs for a reason, because they're easy to hold on to, all that jazz. I want the inner circle of this to be 2.8 millimeters. Extrude, extrude, distance to object of the bottom of the servo, and I want this to be a new component. So now I have this standoff. I can Control C, Control V, and then use move point to point, move this circle to any given point if needed. So now I could do all 6 of these, and now this is how I could have a nice stable base for myself, and this entire thing can be fabricated in like 20, 30 minutes total. And I'll just use a handful of screws. And of course you can keep going on with stacking 2D profiles, stacking servos, and all that stuff. Something to note is that servo horns like wobble, so they're actually not that stiff. So what one might actually do instead is, let me just real quick select all these parts. And I can't select that because I think it's a body right now. So select components, move, select all this. Let's move it to the side for a second. Because what is probably more optimal here is instead use the gear command and have it be done with a gear that is rigidly affixed. And this is the part where we'll start going into more like better traditional design. So this is not a good robot arm at the moment because having it just sit on the servo horn is not very stiff, not very strong at all. I'm sure you've experienced this if you ever worked with servos before. It's not very strong. So you want the entire system to be as strong, as stiff as possible. What you could do is use add-ins, scripts, and add-ins. And then there is a gear command somewhere here. Here's the spur gear command. Let's create a spur gear real quick. 300 millimeters too much, so let me just play around with this. Center hole diameter is too large. Let's call the center hole diameter 3 millimeters. And then root fillet diameter, I'll just keep doing what it tells me to do, and then I create a spur gear. So that is one spur gear, and now that actually probably needs to be bigger. So spur gear, let's call that 2, and then root fillet radius, it wants that to be smaller, so let's call that 1. So we have one gear here, another gear. I can put bolt hole patterns on this and affix it to the servo horn like earlier. The other thing I need to do is make sure that the 2 green lines here, I'm not sure if you can see these green lines. These 2 green lines here need to be pretty much touching each other or tangent for this to work. I like to make it as tangent as possible. Just zoom in and then it looks tangent. And now what I'd probably do is move this, and then slot this up. Bolt hole pattern goes to the center of here. And then I would probably just combine this gear and this part, so it's one 3D print in general. One other concern is, now how is this gear going to exist without while being rigid? So what you could do is, as part of the gear geometry, I'll just isolate it real quick, or actually need to delete it. Control C, paste new. Because if I modified the first gear, it would end up modifying the second gear, so I need these to be independent parts. So let me isolate this. And then what I'm doing here is giving it a effectively bearing surface, which will help me. So this distance to object down here. Join, I don't want it to join that, I want it to join the gear. And then I'm going to give it a little bit of a fillet here, because the fillet means there's less surface area, less friction, which means it'll last longer as a part. I actually might need this to be 2 parts. What I can do now is either do one of 2 things. I can put a ball bearing in here. So let me just guess a ball bearing dimension. So this, I believe, is a normal ball bearing dimension. Let's call this, I think this is a 608 ball bearing, and we should have these on hand. Now what you could do is, actually this probably needs to be offset a bit more down. Does that work? No. So let me scroll all the way to the end, edit this, or sorry, edit this one, let's call it 30 millimeters. Have this go down here. And then move this down. And then what you could do is now you can find a bolt of some sort. This bolt would have a 10 millimeter diameter with like a 18 millimeter head or something. I don't actually particularly remember. That bolt would constrain everything down to the base plate. Or I guess then I create the hole here to object. There we go. So now a shaft can go through this entire ball bearing system, and you can use a nut to constrain everything at the bottom. So everything can rotate around and be all good and stuff. So this should be more rigid than what you're doing with just this alone. And of course, now this looks like it's rubbing, so I can just cut that off a bit. So now this robot arm might work, but if I want to rotate this joint up, then it might catch the gear still, so I'm going to make this more rounded so it won't catch the gear, and I actually might need to make this gear a little bit shorter too. And again, I only want to cut one of the gears, not both of the gears, so I'm going to deselect one of the gears. Okay, I think that's right. Okay, so now this is, in theory, this would work. This part, this yellow part would be a ball bearing, and this, what is this? Why is it such a weird shape? Oh, that's the head of a bolt. And then let me just finish off catting the bolt. So this would be the bolt, and then you'd have a nut that goes through. The bolt would act as your shaft. This is a quick and easy way to do a bearing surface. Of course, you don't even need a ball bearing. You could just deal with the fact that it's plastic on plastic. There's a couple ways to make it low friction plastic on plastic. You can take a pencil, because pencil is graphite, and like rub it along the shaft, and that reduces friction a lot. Use oil. You can sand it down until it's like a good fit. That sort of stuff. There's things up here if you need standardized components like MakeMaster car parts or screws. So say I need like that M10 bolt, I could just grab it from MakeMaster car and toss it in here. So product detail, scroll down, I go to 3D step, and I can just download it and it'll pop up somewhere, right? So now I have this a screw, and I can move it into position if need be. I think that is mostly the things I want to go over today. I'm jamming a lot of things in 1 hour of like how to CAD fast, how to do things fast. I'm missing a lot of things, of course, but yeah, for stiffness things, you can add fillets wherever needed. Fillets help reduce stress risers and make things slightly stronger. So this fillet, although it's small, could help, and I could make it bigger if I need more strength. Okay, cool. Does anyone have any questions? Any thoughts? Is there something that you want to be able to model and that I haven't gone over in this today? Yes.
Wait, can you go over like how you got the gears?
Yes. So Fusion 360 has a gear generator standard to it. You can utilities, add-ins, scripts and add-ins over here, and then you can generate gears here by clicking this little like triangle thing, and then you put in the numbers that you want. Usually I just go for metric. A higher pressure angle, like 25 degrees, is sometimes stronger. As long as your gears have the same module, they will always fit together. So even if I keep the module on 2 and then change down to 12, it will fit with the other gears I've designed because these were also module whatever I need it to be. And I can just drag them and then have this happen. The module is effectively the spacing of the gear tooth. So let me show you, like, does it say here? So let's say the module, let's say the module is 4, in fact. Module 2 gear versus a module 4 gear with 12 teeth, you can see what happens here, right? Okay, cool. Any other questions?
Yes, maybe the slicer. Do you have time to go over?
Yeah, I can go over the slicer. So most of our 3D printers are Bamboo 3D printers. So the ones that you'll have access to will either be Bamboo or Prusa. More than likely it'll be Bamboo. So I'll talk about how to put a file in here and how to optimize it for 3D printing and stuff. Yeah, no problem. Okay, so this is the slicer. The most common one will be Bamboo Studio. So let's see. You'll see A1s and X1 carbons everywhere, 0.4 millimeters. The generic PLA stuff is fine, generic, whatever. So you can insert a part. Let's say I want to insert, which one of these is a relevant part? Stepper motor mount. This looks like a 3D printed part. So this is in the slicer. I imported the part. I have it here. What I like to do immediately is click here and click here. This one aligns the face of the part to the most optimal printing geometry, and this one aligns it so if I have multiple parts, like in one sitting inside the other, this button over here organizes them. What you can do to optimize 3D printing, depending on how much time you have, is first of all, always gyroid infill is a good like to-go infill. It is the best balance of strength and print speed. If you're most concerned about just raw strength, there is honeycombed infill or adaptive cubic are better for like the weight to strength ratio, but gyroid is like the best balance of weight, strength, and print speed. If you want a part to be stronger, instead of increasing infill, you want to increase walls. So walls increases strength more than infill does. What infill actually does is keep the part from collapsing. So if you imagine of a cube, 10% infill, I can just squash it in the Z direction. 100% infill, I won't be able to do that. But if I need it to be strong in every other dimension, like this has a lot of interesting dimensions, I would increase walls. So let's see what that looks like. I click slice plate. This is 4 walls rather than 2 walls. And then I kind of just, let me drag this through. You can see increase of walls makes it stronger at the end of the day. Let's say now that this is a weird print geometry. Like, for whatever reason, I need to print it this way. You need supports for this. You need to enable supports here. So tree support is the default. I'm also going to turn off advanced because most of the time you don't need that. Tree support is like the go-to support because it's easiest to break off. And it'll be the default on the printers. Select slice and then you can see what happens. Supports are needed because you can't print over thin air. So you need to print on something. So you can see how the support kind of helps support the part. Intuitively, I know this because I've 3D printed a lot, that this part won't stay on the bed. So you need a thing called a brim or support. So I'm going to go to the others tab and increase a brim, outer brim only, and I'm going to increase it to like 10 millimeters or something. This gives it more surface area to stick to the bed and hopefully be a little nicer. What I like to do is rearrange it with this rearrange tool. Slice plate again, and hopefully a brim generated. Okay, nice. So this brim increases the surface area because the point of contact here is like incredibly small. But you can see this is how you could go ahead and 3D print. If you need things to be like even faster, but still decently strong, you can decrease infill even more, increase walls, or click on one of these and go to draft. This decreases quality, but will increase print speed. So now let's see, these 2 parts would take 3 hours, but if I was on the standard, these 2 parts would take that, I don't, don't know how that happened. That's actually so much faster than this. Well, I mean, you can always play around with this. It's actually, oh, it's because this is grid infill, I think. No, that's actually pretty surprising to me. That a larger nozzle means that speed is, yeah. But you get the idea. Play around with settings, get the speed down. If you really need speed, the best infill for speed to strength ratio is not gyroid. In fact, it is lightning infill. Lightning infill should be faster, but it compromises strength, but not terribly much. So again, the best balance is gyroid infill. The best speed to strength ratio is lightning infill. The best strength to weight ratio is like adaptive cubic, or that's just the highest strength in general is adaptive cubic or honeycomb. Okay. Cool. Any other questions? I've been looking at the stream. Okay. Okay, cool. Thank you all for coming. We have a KiCad workshop in like 2 hours or like an hour or something. Yeah, we have a KiCad workshop in a bit. Come for that. That will be over Zoom, but I'll also be doing like the guy that's running it will be in room, like he'll be over Zoom, but I'll also be running it in room 1-242, I believe. Let me actually check that. Because we actually originally planned for it to be in a room, and I'm not sure if people got that memo. So I'll be in that room helping people with KiCad if need be. Yeah, room 1-242. KiCad is PCB design. We have these things called PCB mills on campus, so you can mill out printed circuit boards. If that makes sense. So your electronics will be significantly cleaner than everyone else's, and will look a lot better. But yeah, that will happen at 8 in room 1-242. But will be primarily over Zoom. I'll just be like bouncing around if people need help or answering questions. So yeah, thank you all for coming.